All right, guys, section 8.3, the inverse of a square matrix. Now, we've already sort of begun the conversation with this, again, with the, like example number 10 yesterday, problems like number 62 off of last night's assignment. Again, those various types of questions. But basically where we were at, when we were asked to create the matrix equation A times X equals B. So what we're inching towards, again, yesterday, again, we were asked to set up the equation, and then we didn't really do much with it, frankly. We just were asked to set it up. And then it was, all right, set it up, and then go back to what you normally do, create the augmented matrix, and do row operations, and all of that fun stuff. Okay, yeah, and we were able to pull it off. Like I said, we just did number 62, and that was definitely the larger type of question. If the goal is to solve for matrix X, to figure out what is matrix X, because going into it, if I'm given the system, I know exactly what matrix A is, and I know exactly what matrix B is. Okay? We don't know matrix X, which is a really good reason as to why we call it the variable matrix, right? It's the matrix that has all of your variables. That's what you're trying to solve for. So if we were to think about, again, and I'm pretty sure that we talked about this yesterday, but if we were to think about this algebraically, guys, sure would be nice if we could just come over here and divide both sides by A. They would cancel out on the left, and X would be equal to B divided by A. That would simplify our world significantly. Unfortunately, there's a flaw in this thinking. Does anybody know what that flaw is? Yeah, there's no such thing as division of matrix. Okay? So again, off to the side here, I'm going to go off on a little tangent. You'll realize in a second why that's such a terrible joke. But if we had something like the tangent of X is equal to 3/4, something like this, that would be just as ridiculous if we said, yeah, no problem, just divide both sides by tangent. Tangent's not a number. So how could you divide by tangent? Or it'd be like if you had the square root of X equals 3. And you said, yeah, just divide both sides by the square root. Like, that doesn't make sense. You can't do that mathematically. Like, it's literally not possible. I hope that looks ridiculous to everybody else, right? Okay, it'd be the same thing over here. We can't just divide both sides by tangent. That's not a thing, okay? Tangent is an operation. So how can we get rid of tangent if that's the goal? We know that we're going to apply what? Tangent inverse. The catch is that if you do it on the left, you have to do it on the right. So that's how we would go about isolating the X. So we understand how these inverses work. We've been using them literally for years. So if I wanted to get rid of A, we're going to have to figure out this whole idea, this notion of a matrix inverse. Same catch. If I multiply the left side by A inverse, what do I have to do on the right side?
A inverse.
We're going to have to multiply by A inverse. Now there's a little bit more to the story. It's not so much that these cancel out and they disappear. When we multiply a matrix by its inverse, we create what we call the identity. The identity multiplied by a matrix never changes it. So for our purposes, we're thinking, yep, we're canceling that matrix out. So actually a little bit more to the story that we'll get into here in a minute. But this is how we're going to go about solving for matrix X. This is how we're going to get there. Now, in order to pull this off, what do we need to know how to do? We have to know how to find an inverse, right? So the good news is that depending on the size of the matrix, and you got to go, all right, smile nicely. Yeah, just like that. If we were to have a 2x2 matrix, finding the inverse of a 2x2 matrix is really not that bad. We're going to show you two ways to pull this off. We have the row operation way. We also have a formula that we're going to introduce. By the time it's all said and done, I'm sure that most all of us will prefer to use the formula on the 2x2s. Where it's a real hassle is when you go to the 3x3s, because there's no formula. We have to do row operations, and those problems they're large. There's really no way around it. They're just bigger problems. More steps required. If you're trying to get into reducer echelon form, that's 9 pieces that we've got to get right.
This is going to be the last club photo of this period. At 9:50, in the next 2 minutes, you should be heading down if you are in Unified Bowling, Circle of Friends, Upward Bound, Republican Club, and Athletic Trainers. 9:50 in about 2 minutes.
See you later,
head
Robert.
down if you're in Unified Bowling, Circle of Friends, Upward Bound, Republican Club, or Athletic Trainers.
No problem.
Thank you.
All right, so guys, our goals for today, students will be able to verify that two matrices are inverses of each other. Number 2, students will be able to use a formula to find the inverse of a 2 by 2 matrix. And then finally, number 3, students will be able to use inverse matrices to solve systems of linear equations. All right, all a whole bunch of words for the time being. All right, so where we're at right now, we've got 2 matrices that we need to introduce. And I suppose, unfortunately, they sound really familiar. We have the identity, and then we have the inverse. They both start with I. I mean, they don't really sound the same, but they support one another. So the identity matrix, if we were to look at the identity matrix, it has to be a square matrix. Again, that part's non-negotiable. The number of rows is equal to the number of columns. And it's going to consist of positive ones on the diagonal and zeros everywhere else. So would we say that this is the same as reduced row echelon? Close, but not quite. This is the left side of an augmented matrix that's in reduced row echelon form. But if we're reduced row echelon, like I said, we're augmented, and we've got some other stuff over here. That's, basically taking the place of our answers. So again, if we're just thinking about the left side of a reduced row echelon, that's what we refer to as the identity. Now, the nice thing about the identity, okay, let's think back to, again, use some fancy words here that probably were not quite introduced this way back in pre-algebra or prior to that, but we have what we call the multiplicative identity. Sounds really fancy. All that means is that 1 is the multiplicative identity because if you multiply anything by 1, it stays the same. Not an earth-shattering concept there, right? Whatever number you're thinking about, multiply it by 1 and it stays the same. Same goes with any 3 by 3 matrix here. If you have a 3 by 3 matrix and you multiply it by this 3 by 3 matrix, this identity, it will stay the exact same. Okay? If you don't believe me, go through it and actually do the multiplication. Row 1, column 1, row 1, column 2, row 1, column. You're going to realize that all those zeros and all those ones, the one's going to keep the correct things the same. The zeros are going to cancel everything else out, so you keep the same piece. All right? Any 2 by 2 matrix that's multiplied by its identity. The 2 by 2 matrix identity would just be 1, 0, 0, 1. That's what the 2 by 2, again, we would call that I sub 2, like we call this one I sub 3. Again, I'm sure that you could envision what I sub 7 looks like. I don't want to draw it up because I'm sure that you know what it is. All positive ones on the diagonal, zeros everywhere else. But if we're calling it I sub 7, how many rows and columns do we have? We would have 7 rows and columns. Okay? So again, the whole concept or notion of why the identity matters is that if I were to multiply the identity times a matrix of the same order, number of rows and columns, that is going to stay the same. So for our purposes, if we cannot divide out matrices, the next best thing is to create an identity instead. Okay? All right. So kind of a special note here. We've talked about this quite a bit, that the order is really, really important. When I say order this time, I'm not meaning rows and columns. I'm saying if you multiply A times B, that's not the same thing as multiplying B times A. It does not work that way, except for when you're talking about the identity. The identity times the matrix is going to stay the same, or the matrix times the identity will stay the exact same. So in this case, the order doesn't matter. Okay, the order does not matter. All right, so the inverse of a square matrix. If we were to let A, so our matrix A, it's going to be an n by n matrix. So again, it's a square. Rows and columns are the same. And then we want to let I sub n be the n by n identity matrix. If there exists an inverse matrix A inverse, then all right, all of this is just leading towards saying the same thing. If you have a matrix, doesn't matter. It has to be a square matrix. But again, it doesn't matter if it's 2 by 2, 5 by 5, 37 by 37. If you have a square matrix and you multiply it by its inverse, you will get the identity. So that's how we check. If you're given 2 matrices and it says to verify that they are inverses of one another, or verify that this is the inverse of that, or determine whether this is the inverse of that, we're going to multiply them together and we should get the identity. Does that make sense? That's how we check to see whether or not, again, given 2 matrices, are they inverses to one another? That's how we would go about it. Once again, you're going to notice that the order here does not matter. A times A inverse or A inverse times A. Either way, we're going to get the identity. Okay? So a lot of those rules that we were so adamant about yesterday, how it's all about the order, pay attention to the order. When you're multiplying, the order is a big deal. Now that we're talking about the identity, this is, or the inverse, excuse me, this is absolutely a special case. right? Absolutely special case. So I think that we've already hit on this, but a non-square matrix cannot have an inverse. Again, there's just no other way to say it. If we have an inverse, it absolutely is coming from a square matrix. Okay. Second piece here that's also worth mentioning is that not all square matrices will have an inverse. In fact, this is a pretty special thing. Like I said, this is the special case. This is a big deal for us. Okay. So if we have what we call an invertible matrix, fancy way of saying a matrix with an inverse, it has to be a square matrix. Not all square matrices are invertible, though. Okay, so we want to showcase or take a look at the directions here first. It says, show that B is the inverse of A. Reading those directions again. Show that B is the inverse of A. They're already telling us that they're inverses, aren't they? Like they're telling us, hey, this should work. Essentially, it's like they're saying, prove it. So do we understand that our answer is not going to be the last line, 1001? Like, we understand that's not our answer. Our answer is going to be all of the work that we show to get there. Okay? So what we want to do, if this is going to be true, what we need to show is that A times B is equal to that identity of the 2 by 2 matrix, which is going to look like this. So that's my target. That's what we're trying to create. So if we were to do the math here, multiplying, I suppose, A times B. All right. First off, can we do it? 2 by 2 times the 2 by 2. Can we do that? Sure. We're going to get a 2 by 2 matrix. All right. So with your help, row 1, column 1. Row 1 times column 1. All right. So 4 times 4 is 16. Second element is 5 times negative 3 is negative 15. Good. All right. Row 1, column 2. All right. First element's 4 times negative 5 is negative 20. Second element's 5 times 4 is 20. All right. Row 2, column 1. First element's 3 times 4 is 12. 4 times negative 3 is negative 12. Lastly, we have row 2, column 2. First elements. We have 3 times negative 5 to get negative 15. Second element is 4 times 4 is 16. And as expected, A times B, we're getting 1, 0, 0. So, to stress, this is not my answer. All of this stuff over here, that is the answer. That's how we're showing. And again, I'm fully aware that most of us are probably saying, yeah, but Clevenger, I do this stuff in my head. I agree with you. I would have done that in my head too, but not on this problem. When you have to show, again, this would have been like, and again, I only laugh because I used to teach honors geometry for a lot of years. This would have been like you opening up your chapter 5 geometry test, and it says to prove that triangle 1 is congruent to triangle 2, and you don't show any work, you don't put any steps, you just say triangle 1 is congruent to triangle 2, and then your reason is in my head. Like, no, that's not a proof. Again, that's what we're essentially doing here, is we are trying to show exactly how or why we got there. All right? So finding the inverse of a square matrix. The easy part was what we just did. If we're given if we're given two matrices that says show that this one is the inverse of that one. It's just a multiplication problem, and we know what the target is supposed to be. Where it gets a little bit more complicated is if you're given a matrix and now it says, all right, now find its inverse. We've got to go about figuring that out. So we have some steps here, frankly, some concrete steps that as long as you follow this, this first, second, third step, you're going to be very successful with this. But first thing we want to point out is that if A is a square matrix of the order n by n, then we're going to do these things. All right, so that first part has to be a given. It has to be a square matrix. So step 1 is that we're going to set up an augmented matrix with A and the identity of the like size. So let's just making this up here. If we have matrix A, I'm going to be as boring as possible. If we have 1, 2, 3, 4, that is my matrix. It says that we're supposed to create A, so 1, 2, 3, 4, augmented with the identity, so that'd be 1, 0, 0, 1. Does that make sense on the setup? That's the first thing that we have to do. From here, we're going to convert the left side into reduced row echelon form. Okay? So that means that we want to do our row operations, work our magic to make it look like this. Now, as we're doing all of those steps, aren't we going to be getting different numbers over here? Yeah, well, when